The history of the cosmos is written in light. For more than 4 centuries, our mission has remained the same: to read the electromagnetic spectrum and uncover the laws that govern the universe. In 1672, Isaac Newton laid the foundation. He demonstrated that white light is a composite of many colors, and that the prism simply separates intrinsic components already present in the light. But the spectrum soon proved wider than the human eye. In 1800, William Herschel discovered infrared radiation, revealing a new wave band essential for thermal measurements and molecular spectroscopy. Later in the 19th century, Gustav Kirchhoff and Robert Bunsen showed that absorption lines correspond to emission lines of the same substance. This breakthrough gave birth to astrophysical spectroscopy, the ability to determine the chemical composition of stars. In 1900, Max Planck resolved the black body radiation crisis by introducing energy quantization. His constant, h, became a cornerstone of modern physics, proving that energy is exchanged only in discrete packets. A few years later, Niels Bohr introduced the quantum model of the atom. Spectral lines became direct signatures of quantum jumps between discrete energy levels, allowing us to map atomic structure. And soon after, Arnold Sommerfeld expanded Bohr's model by incorporating relativity and elliptical orbits. This explained the fine structure of spectral lines, showing that high-resolution spectroscopy reveals fundamental physical constants. In 1917, Albert Einstein formulated the theory of stimulated emission, the mechanism that would later make the laser possible. From this moment onward, humanity gained the power to control light with unprecedented precision. Still, in the early 20th century, Chandrasekhara Venkata Raman discovered the Raman effect, granting access to the vibrational fingerprints of molecules through inelastic light scattering. A fundamental step in the affirmation of spectroscopy arrived in the mid-20th century, when Gerhard Herzberg transformed the discipline into a mature, predictive science by systematizing complex atomic and molecular spectra. Then, spectroscopy expanded into a new dimension: space. In 1973, Paul Lauterbur introduced magnetic field gradients to spatially encode nuclear spin signals, leading to magnetic resonance imaging and making spectroscopy a revolutionary tool in medical practice. And by the end of the 20th century, Ahmed Zewail opened the femtosecond frontier. With ultra-fast spectroscopy, he captured the making and breaking of chemical bonds, filming molecular transformations in real time. Turkish scientists also played prominent roles in this odyssey of discovery. Beginning in the 1960s, Oktay Sinanolu developed pioneering theories of electron correlation, providing the rigorous framework needed to interpret increasingly complex spectra. And in the 2000s, Engin Arik extended spectroscopic methods into the tera-electron-volt regime at CERN, where high-energy particle distributions are measured in the search for new fundamental particles. Today, spectroscopy is everywhere, shaping chemistry, biology, astronomy, and medicine, and opening new windows into the unknown. With advanced experiments, powerful computation, and ever-increasing precision, we can now observe matter at its most fundamental level, from the smallest molecular motion to the vast architecture of the cosmos. Spectroscopy allows us to trace energy, identify the building blocks of life, and search for signatures of worlds beyond our own. This global scientific journey continues to expand at the frontiers of discovery. Peter Atkins is an emeritus professor at the University of Oxford. He is one of the most influential voices in theoretical and physical chemistry. He has shaped the way several generations of young students and researchers understand the fundamental laws that govern matter. His deep insights into the fundamental rules of physical chemistry have strengthened the conceptual foundations of the spectroscopic interpretation of the universe.
Professor Jan Lundell is a leading expert in molecular spectroscopy and low-temperature physical chemistry at the University of Helsinki, Finland. His research focuses on light-matter interactions, noble gas compounds, matrix isolation spectroscopy, and weak intermolecular interactions, combining experimental and theoretical methods to study molecular behavior under controlled conditions. He also serves as director of Luma Center Finland and is internationally recognized for his significant contributions to spectroscopy and chemical research.
Malgorzata Baranska defines bioanalytical spectroscopy. She applies molecular fingerprinting to living systems, bridging chemistry, biology, and medicine through non-invasive imaging. At the computational frontier, Weitao Yang, professor at Duke University, revolutionized computational spectroscopy by developing linear scaling density functional theory. Today, this approach enables simulations of molecular systems containing thousands of atoms with unprecedented accuracy, pushing computational spectroscopy into a new era.
Professor Mustafa Soylak, a member of the Turkish Academy of Sciences, TUBA, is a distinguished analytical chemist at Erciyes University, Turkey. He is internationally recognized for his contributions to chemical sciences. He has received major honors, including the TÜBİTAK Encouragement Award, TÜBİTAK Science Award, and the İlim Yayma Award, and has been supported by the TÜBİTAK 2247/A National Outstanding Researchers Program. Professor Soylak has authored numerous scientific publications and continues to contribute to the field through research, academic leadership, and collaborations.
At the molecular scale, Rui Faustul, professor at Istanbul Kültür University and at the University of Coimbra, has demonstrated how spectroscopy can uncover the pathways through which energy flows inside molecules and how quantum mechanical tunneling can be accessed and controlled. As the European Research Area Chairholder at the Istanbul Kültür University Spectra Center, his work integrates advanced quantum modeling with precision spectroscopy experiments on isolated molecules and crystalline systems, contributing to shaping the future of molecular sciences in Turkey. As spectroscopy has evolved from its origins to the frontiers of modern science, the Istanbul Kültür University Spectra Molecular Sciences and Spectroscopy Applied Research Center stands as part of this continuum, where past insights meet future discoveries. From Newton's prism to the IKU-SPECTRA, Molecular Sciences and Spectroscopy Applied Research Center, spectroscopy has become a universal language through which we understand the universe. And the next great discovery may begin here, with you.